Have you ever seen something that just didn't make sense? Something that seemed to defy all the rules you thought you knew? Well, back in the late 1800s, scientists saw a strange little spark that did exactly that, and it would take one of the greatest minds in history to figure out what it meant for the very nature of light itself.
What they stumbled upon is called the photoelectric effect. And it sounds simple enough, right? You shine a light on a piece of metal and zap! Electrons, the little particles that make up electricity, get knocked right off the surface. But the details? Oh, the details of this effect were about to turn the world of physics completely upside down.
So how did this whole thing start? Well, like a lot of great scientific discoveries, it didn't begin with some grand theory. It started with just a simple, curious observation. Okay, picture this. It's 1887, and a physicist named Heinrich Hertz is messing around with electricity. He notices something really odd. When he shines ultraviolet light on a charged piece of zinc, it loses its charge. Now, the only way that could possibly happen is if the light itself was physically knocking tiny, negatively charged electrons right off the metal. The question was, how? So, to get to the bottom of this, scientists built these cool little contraptions called photocells. Basically, you shine light on a metal plate inside a vacuum, and you can actually measure the electric current made by those escaping electrons. And it's this setup that revealed just how bizarre this whole thing really was. And this is where the story gets really good, because the results coming out of these experiments made zero sense based on the physics everyone knew and trusted. The rulebook was about to get completely shredded. See, back then, everybody knew light was a wave. Think about a wave in the ocean. Its energy comes from its height, right? Its amplitude. So a bright light was just a tall, powerful wave. The prediction then was obvious. Any color of light should be able to knock an electron out, as long as you make the wave big enough, bright enough. This was considered settled science. Light is a wave of energy. Its power is all about its brightness. A dim light is a small wave. A bright light is a huge, powerful wave. Simple. Except reality was about to throw them a serious curveball. So here's the first shocker. When they actually did the experiment, low-frequency light, like red or orange, did absolutely nothing. And it didn't matter how incredibly bright they made that red light. Not a single electron would budge. Only the high-frequency light, like blue or UV, actually worked. There was some kind of minimum frequency, a threshold, and anything below it had no effect at all. And then came the second shocker. According to the wave theory, making the light brighter should have given the electrons more energy, making them fly off faster. But it didn't. Instead, a brighter light just knocked more electrons off the metal. The energy of each individual electron stayed exactly the same. So brightness controlled the quantity of electrons, not their energy. This was a complete and total failure of classical wave theory. It was like saying a giant tsunami can't move a single grain of sand, but a tiny, fast little ripple could launch it into the air. The rules were broken. So what on earth was going on? Well, it took a 26-year-old patent clerk to solve the whole mystery. In what's now called his miracle year of 1905, a young Albert Einstein came up with an idea so radical it would completely redefine our understanding of reality. Einstein's idea was this. What if light isn't some continuous flowing wave? What if instead it's made up of tiny individual packets of energy, almost like a stream of microscopic bullets instead of a river? He called these little energy packets quanta, which we now call photons. And here is the absolute game changer. The energy of a single photon has nothing to do with brightness. Instead, its energy is determined by its frequency, which is its color. A photon of blue light simply has more energy than a photon of red light. Next, Einstein came up with an idea he called the work function. The easiest way to think about it is like an escape fee. Every metal holds on to its electrons with a certain amount of energy. And to pull an electron out, you have to pay that energy fee first. And this is where it all clicks into place. Einstein said it's a strict one-to-one deal. One photon hits one electron. The transaction is dead simple. If that incoming photon has enough energy to pay the metal's work function fee, the electron gets kicked out. If it doesn't have enough energy, the deal's off. Nothing happens. So with just those two simple ideas, photons and the work function, the entire baffling mystery just snaps into place. It's beautiful. Let's walk through how this explains every weird result. So first, why did only high-frequency light work? Well, it's because only the high-frequency photons, the blue and the UV ones,
carry enough energy in one single packet to pay that escape fee. A low-frequency red photon is like trying to buy a $10 item with a single penny. It just doesn't have enough value. And it doesn't matter if you throw a billion pennies at it, the rule is one transaction, one electron.
And this explains the threshold frequency perfectly. The minimum energy you need to escape, that's the work function, W, is exactly equal to the energy of a photon at that minimum frequency. If a photon's frequency is below that threshold, no electrons are going anywhere. It's a clean, elegant, physical law.
Okay, so what happens if the photon comes in with more than enough energy to pay the fee? It's like paying for a $10 ticket with a $20 bill. That leftover energy doesn't just disappear. It's given to the electron as speed, or what we call kinetic energy. The electron gets to keep the change.
And that brings us to Einstein's famous photoelectric equation. And look, it's not scary math. It's just a simple energy budget. The total energy that the photon brings in is split into two things: the price to escape the metal plus the leftover energy that becomes the electron's speed. It's a perfect accounting of energy.
And this solves our very last mystery. What was up with brightness? Well, in Einstein's new model, brighter light doesn't mean more powerful waves. It just means more photons, a whole flood of them. And more photons hitting the metal means more of those one-to-one transactions, which means more electrons get ejected every second. And that creates a higher electric current, exactly what scientists were seeing in their experiments.
So Einstein's theory just worked. It explained everything perfectly, but the implications were absolutely staggering. It meant our whole understanding of light was fundamentally incomplete. So let's look at the final scorecard. The classical wave theory, it failed on every single count. Einstein's photon theory, on the other hand, explained every single experimental result perfectly. The evidence was just undeniable.
And for this incredible insight, Albert Einstein was awarded the Nobel Prize in Physics in 1921. And what's amazing is he didn't win it for his more famous theory of relativity. He won it for this, for explaining the photoelectric effect. That's just how profoundly important this discovery really was.
The ultimate lesson here is that light is, well, it's weird. It leads a double life. Sometimes it acts like a wave, but other times, like in this effect, it acts like a particle. And this strange idea, what we now call wave-particle duality, became the absolute cornerstone of a whole new field of physics, quantum mechanics.
It proved that the universe, down at its smallest scales, is so much stranger and more wonderful than we ever thought. Which kind of leaves us with a final question, doesn't it? If light can be two different things at once, what other rules of our universe are just waiting for us to discover?